Okay, hey people, continuing along, let's take that basic information we learned about vectors and apply that to our content in the discussion of the orbital angular momentum operator. Let's go for it. Let's see. Okay, here we go. So we can see now that hopefully this looks familiar. We've got the cross product here. So orbital angular momentum operator is R cross P that we can see written right here. So recall now the way that this is going to go, right? Our unit vector I is going to be x, excuse me, our unit vector I is going to be y pz minus z py. Our unit vector j is going to be x pz minus z px, and then the unit vector k will be multiplied by x py minus y px. Okay, just making sure I don't have any mistakes in there. So now if you recall, our linear momentum operator is given by the following: h bar over I times first derivative in position, where now this q could be is my position operator in any dimension, x, y, or z. So recall we can also write the linear momentum operator as negative I h bar times ddq. So either one of these works. We'll stick with the h bar over I for now. So what we can also do from here is separate out the individual components of the vector in the x, y, or z dimension. So for example, if I highlight this or if I underline this right here, we can see that will give us the Lx operator. And if we factor out h bar over I from that expression, we can see now we'll have y ddz minus z ddy, right? Remember, that would normally be, y times h bar over I times ddz, but we factored out the h bar over I. I can highlight the j vector, which is our y component, right here, given by h bar over I times x ddz minus z ddx. And then finally, I can note my z dimension right here, given by x ddy minus y ddx. And if you recall, when we did our particle on a ring model, these derivatives give us the change in phi, right? So this LZ model is still giving us that same notion of the right-hand rule, where if the particle moves exclusively in the x and y dimension, it has angular momentum solely pointing in the z direction. Okay. So I want to take us back to our finding from the particle and the ring model, which was that probability density is independent of angle phi, right? And if you recall, that came from taking the square modulus of the particle on a ring model. And recall, we just got this constant from that. So the particle's position on the ring is indefinite. Therefore, angular momentum and angle make a set of complementary observables suspect to Heisenberg's uncertainty principle. So we're going to have to deal with that. So let's recall now the commutator between position and momentum. So this was the linear momentum, right? Was given by I h bar. So now something kind of cool happens if we look at the commutators between any of our respective dimensions. So like, what's the commutator between angular momentum and the x and y dimension? We get I h bar LZ. So right, we're getting that I h bar eigenvalue from the commutator, and then there's an additional times LZ. So now you can see when we switch it to y and z, we get a commutator in the x dimension. And when we switch that to z and x, we get a commutator in the y dimension. So what this means is we can't specify more than one component of angular momentum simultaneously with arbitrary position, right? If we try to do that, we're just going to end up with uncertainty in the other dimension. So what about the magnitude of angular momentum? Well, again, going to our properties of vectors, here if we look at the overall magnitude of our orbital angular momentum operator, that's going to be given by the following, and technically this is the square of that angular momentum magnitude, right? So that's why the square root is missing. Well, if we were to go through that, we would find that has a fairly simple result to write, h bar squared times the Legendran squared. Obviously if we plugged in the Legendran, that would be a little bit more complicated. But all the same, now we have an operator for the magnitude. And now if we were to look at the commutator between the overall magnitude and any one dimension, we can see that they do commute, so that there is no uncertainty there. And so I could replace that Q with any one of those angular momentum components in the x, y, or z dimension. And when I compare that to the overall magnitude, they commute. So there's no uncertainty between them. So this creates an important distinction here. So although we may specify the magnitude of angular momentum and any of its components, if LZ is known, then it is impossible to describe values to the other two components. And we're just picking LZ arbitrarily. So arbitrary. And we picked the Z dimension arbitrarily because of our right-hand rule, right? When our particle is moving in the x, y dimension, we have uncertainty in its angle phi, but we know with great precision its angular momentum and its magnitude. So that's going to be important as we look at the next model in this problem, which is commonly referred to as the vector model. And we'll talk about that in the next video, folks.